Hi guys, today's video is about the LSI SAS 2008 chipset. This is an I/O SAS controller chipset that was released sometime, I believe, in 2011, so it's about 7 years old now. And it was widely deployed in a lot of different variety of controller cards. As you can see here in this Google image search, a lot of HBA Mega RAID SAS controllers, onboard controllers on motherboards we're using this chipset, some mezzanine cards for certain servers, and even SSD PCI cards use this controller as kind of a flash accelerator type of device. So this is a very widely, very successful 6 gigabit SAS controller that's used in a lot of different applications for a very long time now. And in spite of it being 7 years old or so, it's still widely used today. And so I wanted to do a performance overview of what can this SAS controller do 7 years after its release in 2018. And so today I'm going to run some benchmarks on a couple of different setups. I have the spreadsheet here prepared for the different type of setups. So I'm going to, first of all, just to kind of get a baseline, I'm going to run the benchmarks and I'll talk about what we're going to do with the benchmarks today. But on a single disk, and it's a Hitachi SAS 4TB hard drive, and I have 16 of these in the server that I'm going to use today for this video. And then I'm going to then repeat those tests on 8 hard drives, 8 of these 4TB hard drives in a RAID 0, and on a single controller. So in the server, you'll see later on that I actually have 2 LSI SAS 2008 controllers. But I'm going to put 8 hard drives on one of them, and I'm going to put those 8 hard drives in a RAID 0. And this is just to kind of see what the total potential is on a single LSI SAS 2008 controller. But I also have a second controller, and so I'm going to do the same thing across 16 hard drives in a RAID 0 and see how much more do you gain when you use 2 controllers. And now RAID 0 is nice just because there's not a lot of overhead and you can kind of just see the full potential of what's possible. But it's usually not a very practical setup for a lot of situations because there's absolutely no data protection. And so after doing the RAID 0, I'm going to do probably something that's a little bit more typical. We're going to use ZFS and we're going to do a RAID Z2, so it's basically equivalent to about RAID 6 on 8 hard drives again on a single controller, and then we're going to repeat that on 16 hard drives across 2 controllers. And then we're going to do 2 different RAID Z2 sets together, kind of striped over those 2 sets. So it's going to be 2 sets of 8 hard drives striped together into one single ZFS pool. So we're going to see what the performance is like. And now granted, the type of performance testing I'm going to do today is very limited. It is just to get a broad idea of what these chipsets are capable of 7 years after their release. It's not comprehensive. There are obviously very different types of I/O use cases. Whether you're running a database to doing a file share with large files versus small files, and whether your I/O patterns are mostly sequential or random. And so anyway, there's a lot of different scenarios you can test for. So these benchmarks do not apply to all situations, but it'll give you a broad sense again of what this chipset is capable of today. And in order to run these tests, you kind of have to pick a particular type of test you want to run. So for one, I'm going to focus on 1 megabyte records. And that's not the typical. You'll see a lot of tests that run like 4K or less. And there's certain, again, benchmarking is kind of an art form. You kind of have to decide, what are you testing for, what use case are you interested in. But I'm focusing on 1 meg just because a lot of the systems that I work with and a lot of people who buy HBA controllers from me are building file servers to store their home media. And so that's a lot of large files that are sequentially read when they're being streamed and whatnot. And so I'm going to really focus more on that type of use case. So this benchmark is kind of more geared towards that. But I'm also going to do some testing with random IO here, as you'll see in the last 2 columns here. But anyway, just to describe, why I'm picking, that's why. I'm going to run a DD sequential write and sequential read. So this is a very common, simple benchmark. It's it's not the most sophisticated thing to do, but it is something very simple. And so I suspect a lot of people do this just to kind of get a basic idea of if their disk system is working correctly or not. So that would be nice to just have something to compare to. And one of my favorite benchmark tools is IO Zone. It's a very sophisticated, very capable and very versatile IO benchmarking tool. And so I tend to prefer to use this in a lot of benchmarking scenarios. But what I'm going to focus on is sequential writes, sequential reads, and then random writes and reads, again at 1 megabyte record sizes. So today we're going to run these tests across these different scenarios, and we're going to plot them in this spreadsheet here, and we'll see what we get to at the end. All right, so let me put this away for now, and I'm already logged into my server. As you can see, I have 16 Hitachi 4 terabyte drives. Now these are the 7K6 generation, so they're not really old, but they're not the latest and greatest either. And also keep in mind that any benchmarking or performance numbers that we see today are specific to this setup. So if you have older hard drives that are a little bit slower, perhaps you're not going to get similar numbers. And if you have much more modern hard drives that are a little bit faster, you might get slightly better numbers. But just keep that in mind if you're trying to compare what we get here today to your own setup. So okay, we have 16 hard drives here, and just to show you what I've got here, I have 2 LSI 2008 controllers here. And so you'll see here the one that starts with 7, this is all on one controller, and then the ones that start on 8 are on the second set of controllers. Alright, so just for starters, let's get some numbers on a single hard drive just to kind of get a baseline of what these hard drives can do. And so let me just kind of pick one here. I'll pick the first one. We'll go ahead and clear this out, and let's see. Okay, so let's go ahead and make a new partition. Primary, I'm going to format it with XFS. I'll use the whole disk. Okay, so now we have a partition. Let's see if it's there. Okay. All right, right there. So let's go ahead and format this. And I'm not going to do a whole lot of different tuning that's available. I'm just going to kind of more or less pick the defaults here. So let me just force that. Okay, so while it's formatting here, there's a lot of tuning you can do in terms of software RAID, in terms of the chunk size, and so later on when we get to the RAID sets, and then also as far as file system formatting and how you mount it and so on, there are various different options that you can choose to kind of bias the your RAID set or your storage pool towards a particular use case. Maybe you're doing something that prefers very fast writes and slower reads, or vice versa, whatnot. There are things you can adjust, but for now, just because I'm trying to keep this simple, and there's just so many factors you can tweak, I want to keep it simple to mostly the default settings. And that way, you know, we'll have something to talk about that gives you kind of a starting point of, you know, what you can expect out of a 7-year-old SAS controller chipset. Alright, so in this other window here, I'm going to run IOstat so we can get an idea. Let's see, where is SDB? Okay, right here. So this is the one that we're going to look at. And I also have top running here. And this just gives us an idea of, like, you know, this is actually a very, very low-end machine. Just to kind of give you an idea, here's the CPU. So it's an L5630, relatively old Xeon processor, just a single socket machine. It's got 4 cores, 8 threads with hyper-threading, and also very little memory. So about 4 gigs of RAM in this machine, so very, very low memory, which is not ideal. This would not be the way I would deploy, for example, a ZFS file server. But the nice thing about having very little memory is also that you can minimize your caching effects. And so, you know, that way our numbers are really reflecting what the I/O subsystem is capable of versus, you know, I/O that's actually hitting the RAM. But we're also going to take extra steps to make sure we clear any caches and so on. I'll show you that in a little bit here. All right, so our formatting is done. Let's go ahead and mount this disk. We've got a directory called data1. That. Oh, all right, let's just do that. Okay, so we have it mounted in data1. And let's go ahead and get started with a DD test. So we're going to do DD. I'd like to see what's going on, so I'm going to do status equals progress, and we're just going to read in a bunch of zeros, and we're going to write to the local disk. Okay, and again, I'm going to do 1 megabyte record sizes, and let's just go ahead and do 10 gigabytes here, and you'll see. So a couple things to notice here. We're going to see DD start spinning up, so you'll see it in the top, and then you'll see that this free memory here is going to get reduced because some of this stuff is going to get cached. But on the first write, it's just entering cache, so we're not going to see the effects of the caching. But then we're going to reduce this. We're going to drop the cache afterwards. So anyway, let's go ahead and do this. Invalid number. Is it capital M perhaps? Oh, there we go. Okay. So you'll see over here in IOstat, we're doing roughly 180, fluctuates probably between 180 to 200 megabytes per second writes. And because the initial write was entering cache, as you can see the memory here, the free memory has dropped down dramatically, right? This actually started a lot faster, but now it's, you know, I think it's calculating an average. So that's starting to approach the numbers we're seeing here. A few more seconds here. So we're getting roughly about 180 to 200 megabytes a second here on this single hard drive. So that's 208 megabytes per second. Although this number is a little bit higher than what we're seeing in IOstat because of the initial caching effect, but we'll just record it as is. It's close enough, you know, for the sake of this kind of simplistic testing. So I'm going to go ahead and record that as 208 megabytes a second in this spreadsheet here. And like I said, I'm going to drop the cache. So you can do this by echoing 3 to this location in the proc file system. And so as I drop this, you'll see the amount of free memory goes back up to where it was before because the cache got dropped. So now we're going to read that same file back and just see what we get for our sequential read test. So I'm just going to dump all this in dev null. Oops. And again, using 1 megabyte records, and then let's go ahead and do that. So we're seeing roughly about the same, about 200 megabytes a second coming from the single disk. And you'll see one thing to make note of here, DDs only consume about 13-14% of CPU. So, you know, the tests we're going to do today aren't extremely CPU intensive, and this is also a low-end machine. But sometimes if you're doing extremely high performance testing, say in multi-gigabytes per second, you need to be aware that, you know, if you have a slow enough CPU, that your testing might be bound by the CPU. So it's always good to kind of look at top or some other CPU utilization statistics here, because if you see this pegged at 100%, then, you know, the numbers might not reflect what your I/O subsystem can handle, but rather what your CPU can handle. So anyway, we got 200 megabytes a second. So let me go ahead and record that. Okay. And let's see. All right. So we're also going to run IO zone on this. So the way I like to run IO zone is first you got to specify kind of the size of the file that you want to use. And I'm just going to do a single thread today, although IO zone is able to do multi-threaded IO testing. But just to keep this simple, and I'm going to pick a 16 gigabyte file. And the reason for that is that I know there's 4 gigs of RAM on this machine, and I figure, you know, 4 times that is 16, and that'll for sure make sure that, you know, our file is exceeding the caching capacity of the RAM on the system. And again, we're going to use 1 megabyte records, and I'm going to run 3 different tests. So this is -I0 is for the initial write test. I1 is for the read test. These are both sequential. And then I'm going to do I2, and this will give us some random IO testing. I'm going to do a single thread, and then this is the stride size. And I like to get some information on CPU utilization, so that's the minus plus U. And I think that's it. Let's go ahead and run this. So while that's happening, again, you can see IO zone not consuming a lot of CPU, so that's good. We know our test is not CPU bound. And IO stat is showing us about 190, 180, 100, almost 200 megabytes per second writes, sequential writes. So this is fairly consistent with what we were seeing earlier with the DD test. And so at least, you know, they're within the same ballpark. I'm just going to wait for this to complete. Okay, so our tests are complete, and we've got some interesting numbers here, but they're mostly consistent with what we saw earlier with DD as far as the sequential tests are concerned. About 200 megabytes per second here for the initial sequential write, and then the rewrite slightly higher. Sequential read is also almost 200 megabytes per second, and similarly for the reread. The random came out to about 80, about a little over 80 and a half random reads, and then about 100 megabytes per second for the random writes. So let's go ahead and record this data here. I'm going to use the average. So the average throughput here. And I'm going to record this in megabytes, so let me just do the conversion. So let's just round that to 195. and then the reads. I'm going to round that to 8 since it was 0.7. Okay, so I'll round that to 196. And oh, wait a second. Did I just... Oh, sorry. Wrong number. Let's use the, for reads, average is this number here. So let's make that 190. And then for random reads, the average here. So we'll say 84. And random, oh sorry, that was a read, so that's actually here. And for random writes, so I'll say 99. Okay, so basically this single hard drive, the Hitachi SAS 4 terabytes, can do about 200 megabytes per second read and sequential reads and writes. Seems to do a little bit better on the sequential writes, which is kind of nice. And then as far as random IO goes, it's about half of that. Alright, so that's kind of gives us a baseline of what the hard drive itself can do. And now let's go on and do something a little bit more interesting. Let's go ahead and make a RAID 0. So I'm going to go ahead and unmount. And let me just go ahead and wipe this drive. Okay, and so of these 16 hard drives, the first thing we're going to do is we're going to create a RAID 0 with 8 of them on the same controller. So I'm going to pick these 8 here. So that's B through I. Alright, so let's go ahead and create dev md0 and RAID devices, if I can spell correctly, is 8. We're going to do RAID 0, and I'm going to leave the chunk size to the default. I'm going to do assume clean so our testing isn't impacted by background initialization, and we're going to do B through I. Yes, go ahead. Alright. Let's make sure. Yep. So, and it picked the default chunk size of 512K. And let's go ahead and format this. Alright. And now we're going to mount this in the Data1 directory. Okay, so we have a 30 terabyte RAID 0 with 8 4 terabyte SAS drives. Alright, let's go ahead and run the DD test on this. So you can see this is obviously a lot faster with 8 hard drives working together. We're getting 1.4 gigabytes per second. And So I'm going to go ahead and record that. So let's 1.4 is 1434, let's say. Okay, 1434 sequential writes, 1434. And as you can see, some of that has been cached, so I'm going to go ahead and drop the cache. Alright, so the memory is freed again, and let's go ahead and do the sequential read test. So about 1.5 gigabytes per second. Let's put that in megabytes. So 1536. So obviously a lot faster with 8 of these drives put together in the RAID 0. And I'm now going to run the IO zone test. Okay, so the testing is complete. Let's go ahead and put some of these numbers in our spreadsheet here. Again, I'm going to take the averages, and so that's, I'm going to round that up to 30 there. So alright, let's alright, so 1470 for the initial write. And here's the average. This is for the initial read. So that'll be 1472. And for the random read, I'll round that to 97. Oh, wait a second. That was random read, right? So that would be this column here, not this one. Random writes. Surprisingly, the random writes is a lot higher than the random reads. So I'm going to round that to 550. Okay, so just looking at the results here so far, having 8 of these hard drives put together in RAID 0 obviously improves performance by quite a bit. If you take the number from a single disk and multiply that by 8, it's actually very, very close to that, especially on the sequential reads here. So, you know, 1536 is not too far from 1600. The random reads, unfortunately, show very little improvement, if any, really. While the random writes are fairly high, actually. I'm surprised at how high that is. I wasn't expecting that to be about 5 times a single disk. But anyway, all right, let's go ahead and do this on all 16 drives and see what kind of performance we get, how that scales up with the drives. Alright, so let me go ahead and unmount that and see. Well, let's see. What did we have here? It was B through I. So MD. Let's go ahead and stop this. And I'm going to go ahead and just clear. Okay. And now let's go ahead and make the same array with all 16 drives. And so that's going to be B through Q. All right. Okay, there we are. And it picked the same default 512K chunks. Let's go ahead and format this. Okay, formatting is done. Let's go ahead and mount this. Alright, so we have ourselves a 59 terabyte RAID 0 with 16 4 terabyte drives. And let's go ahead and run the DD test. Okay, we're about 1.5 gigabytes a second. I'm going to drop the cache, and then let's go ahead and do the sequential read. Okay, so sequential write was about 1.4. So I'm just going to record that as 1434. So actually not a lot of change. So sequential writes doesn't really scale with more hard drives that well at some point here. So that's interesting to know. Now sequential reads, on the other hand, it's 2355. So sequential reads does scale up, but not linearly. It's not like you double it by doubling the number of hard drives, but it does scale up a little bit better than these sequential writes. Alright, let's go ahead and run IO Zone. Alright, so the IO Zone test is complete. Let's go ahead and record these numbers. Again, I'm going to take the averages. So the initial write, so I'll record that as 1676. And for the read, I'll record that as 2139. Okay, so the numbers are pretty interesting here. We know that by adding more hard drives to this RAID 0, using 2 of the LSI SAS 2008 controllers, we can scale up sequential reads It doesn't scale linearly, so at some point it starts to fall off. And the IO zone is showing basically the same results here and here, while the sequential writes plateaus more or less, although the sequential writes in IO zone went up just a little bit, but not by a huge margin. Random writes seems to be scaling fairly well. Strangely enough, it's by doubling the number of hard drives, we got 3 times what we got with a single controller. And so this is actually about 15 times a single hard drive. So this is actually, for random writes of 1 megabyte records, this is actually scaling really well with more hard drives in a RAID 0. Random reads is where we're really not seeing any scaling at all. That's been kind of more or less flat across the board. So, alright, so this is all with RAID 0 with 8 and 16 hard drives, but obviously that's not really the most practical configuration, although this gives us a good idea of what the full potential is without the overhead of things like RAID 5 or RAID Z2 that have parity calculations and other things that have to happen for them to work. So this kind of gives us an idea of what the full potential of the IO controller is. But now we're going to go ahead and rerun these tests on a setup that is maybe more close to what someone would actually do for bulk storage of, say, media files. So I'm going to start with the RAID Z2 across 8 hard drives. Okay, so let me go ahead and stop this RAID array. Oh, I probably didn't unmount it yet. Okay, and I'm going to also clear the super block just because I don't want there to be any potential problems when we do the ZFS stuff. So let's B through Q, I believe. All right. So those are our 16 hard drives. I'm gonna, for the ZFS 8 disk RAID Z2, I'm gonna pick these 8 disks. So let's go ahead and do zpool create and call it data, and it's going to be RAID Z2 from SDJ through Q. Alright, let's just go ahead and force it. Okay, so we have our RAID Z2 pool, and I'm going to go ahead and now create a file system that we'll use for testing, if I could spell correctly. And I'm going to make one change here, or one option. I'm going to pick a record size of 1 megabyte, just so that this kind of matches our testing with the 1 megabyte records. Okay. So now we're on a RAID Z2 with 8 hard drives on a single SAS 2008 controller. We're going to do the DD test first. And I'm going to change, instead of running IOStat, and ZFS has its own IOStat, I'm going to run that version so we can get an idea of what's going on in the pool. Okay, here we go. Alright, so we got 542. Let's go ahead and drop any caches. And we're going to do the read test. Okay, so for the 8 hard drive RAID Z2 sequential writes, we got 542, and for sequential read we got 945. Okay, so obviously with the overhead of the double parity and whatever else ZFS does, it does a lot of things in the background. This obviously is not scaling as well as a plain RAID 0 on 8 hard drives. In fact, for sequential writes, we're getting maybe about 1/3 of that. And for sequential reads, we're getting a little over a half. But it's obviously, it doesn't scale as well, obviously, with the double parity and all that stuff. But this is still very reasonable, considering this is certainly enough. 945 was certainly enough to, say, saturate a 10 gigabit link if you're trying to stream that much information over a 10 gigabit network. Alright, let's go ahead and run the IO zone test now. Okay, so IO zone is complete. Let's look at the numbers here. We're seeing about 450 for the sequential writes. Alright, so I'll record that as 442 for the sequential writes. And for sequential reads, I'll record that as 914. And for random reads, or writes actually, $388. $78. Okay, so the RAID Z2 obviously has more overhead, doesn't scale like RAID 0 does, but it's still fairly reasonable. With 8 hard drives on a single SAS 2008 controller, you can get almost a gigabyte per second reads. That's confirmed with IO zone as well. Pretty consistent results here. The random writes are obviously lower, but still it's scaling up. Now, unlike the random reads, which apparently is really struggling here. So, alright, let's go ahead and do RAID Z2 with 16 hard drives and see what we get next. Okay, I'm going to create another RAID Z2 pool, this time with all 16 hard drives. I'll probably force that. Okay, there's our pool. And let's go ahead and create a file system, and Okay, and let's restart this so we can see. Alright, so let's go ahead and run the sequential write DD test. So that's about 700 megabytes a second right now. Alright, I'm going to drop the cache and let's do the sequential read. Alright, 1.6 gigabytes, so let's go ahead and record that with 16 hard drive RAIDZ2, 694 for the write, and we got 1.6 gigabytes per second, so I'll record that as 1638. Alright, next let's run IOZone. Alright, IOZone is complete. Let's look at the numbers here. We got about 660 megabytes. Let's go ahead and convert, oops. So I'll record that as 651, or 652 rather. Sequential reads, almost 1.5 gigabytes there, looks like. Record that as 1425. And let's do random writes. $641. And 69. Okay, so with 16 hard drives in RAID-Z2 versus 8, we see the sequential writes doesn't really scale up that well. It scales up a little bit, but sequential reads does scale fairly well. Obviously still not as much as what you'd get in the simple RAID 0, but sequential reads, IOZone also confirms that scales up. Random writes also scales up, almost double from 8 hard drives to 16 hard drives, but the random reads still struggle to basically the same performance level as a single hard drive. Okay, so for the last test, we're going to create 2 RAID-Z2 sets with 8 hard drives each and put those together in a single pool. All right. So I'm going to create a new pool, RAID-Z2, with the first 8 drives in its own VDEV there. So that'll be SDB through I, and then another RAID-Z2 pool with the last 8 hard drives. So that'll be SDJ through Q. make sure that looks correct. Okay, so B through I as that RAID Z2, and then J through Q as the second. Alright, and let's go ahead and create our testing area. Alright, let me run IOStat there. Alright, let's go ahead and do the DD sequential write. So far we're seeing about 770-ish. Alright, 763. Let's drop caches and do the sequential read. Alright, so we have 755. So that's actually a little bit on sequential writes. It's a little bit faster than having 16 hard drives in a single RAID Z2. And we have 1.7 gigabytes for that's all. 1.7. Okay, I'll record that as 1741. So having two RAID Z2 sets together instead of just one large RAID Z2 seems to be a little bit faster in the sequential reads and writes. Now let's go ahead and run IOZone. Alright, IOZone is complete. Let's look at some of the numbers we have here. A little over 700. Oops. Wait a second. Alright, so I'll record that as 712. For the sequential read. (1604). Okay, and for random write. 675. And 80 for random reads. Okay, so just to kind of look at the data that we've collected so far, it looks like the 8 drive RAID 0 scales pretty linearly as far as sequential reads and writes go. At 16 drives, it still scales up on the sequential reads, but not linearly. It starts to kind of slow down a little bit. On sequential writes, so sequential writes, it kind of plateaus. So if you look at sequential writes, are basically identical. So that doesn't really scale. Same thing with sequential writes here. Yeah, there's maybe a slight difference there, but it's more or less the same. Sequential reads, on the other hand, does scale with more hard drives in a RAID 0. And then even when you look at the RAID Z2 setups, sequential reads does scale up, although not linearly. It starts to fade. And surprisingly, well, maybe not so surprisingly, but 2 RAID Z2 sets with double parity each. So you would have effectively 12 data drives, because you'd lose 2 drives to parity on each RAIDZ2 set, is a little bit faster than, as far as sequential I/O. Well, let's see. Yeah, sequential I/O and even the random writes is a little bit faster in this scenario versus 16 drives with RAIDZ2. So that's an effective 14 drives with 2 lost to parity is actually a little bit slower. But when it comes to random reads, at least for these this particular test and the setups that we're looking at right now, it really doesn't scale beyond the performance of a single drive. So I'm not exactly sure why that is. Perhaps if somebody watching this has an idea, let me know what you think in the comments about that. I'm, doing this right now, and I'm not really sure how to explain why this seems to be stuck at the same performance level as a single drive. So anyway, there you have it. This is a 7-year-old SAS 2008 controller. They can be had for fairly cheaply, and by the way, I also have a eBay store called the Artist Server, where I sell HBA controllers, ones like this that are pre-flashed to IT mode for those who are building ZFS servers or Unraid or anything that's software RAID. So I'll leave a link in the description to this video to my eBay store. Feel free to check it out. If you have any comments about the testing here, please leave something in the comments, and I'll try to reply. So anyway, thanks for watching, and hope that this was useful. Alright, bye-bye.